So let's recap what we've seen so far. This is Aristotle. Aristotle wrote the book on physics, literally. He is the first to make the distinction between matter on one hand and forces on the other. We still make that distinction today. Now, he thought some things that turn out to be wrong about those forces. He thought that heavenly objects tend to rise. That's what they naturally do. And things that are earthly, like made of water and earth, they tend to stay at rest on the earth. They can move, but they require a constant force to maintain their motion. So said Aristotle. Galileo decided that this was wrong based on his actual experiments. He found that, it's not true that in order for something to keep moving, it requires a force acting on it. In fact, a ball will keep right on rolling without any external force acting on it at all. And he understood that the planets can go around the sun, they can keep right on going, not because a force is pulling them around, but because they naturally tend to maintain motion. Newton came along and perfected Galileo's ideas. Newton's first law says that an object at rest will stay at rest unless some external force acts on it. Also, an object in motion will maintain a straight and steady motion unless some external force changes its motion. Now, to move further and to see what we can do with Newton's laws, we need to understand what mechanics is about. We need to make actual measurements and understand what those measurements are telling us. Mechanics is the study of forces and how those forces produce motion. So to do that, there are three fundamental quantities that have to be used. Three different types of measurements which are fundamental to mechanics. Number one is mass. We have to understand what mass means. Number two, we have to be able to measure distances, so we have to have a concept of length. And number three is time. We have to be able to make measurements of time to do mechanics. So let's start with mass. What is mass? Mass is the amount of matter in an object. It's a way to measure how much matter is in something. It's measured by the unit of kilograms. Kilograms are what we call the metric unit of mass. Now, mass is a measure of how much matter is in an object. It also measures the inertia of an object. Inertia is the tendency of things to maintain their motion. Now, if you push on something, it will start to move. It doesn't just stay in place. It tends to stay in place. How hard it is to get it going depends on what its mass is. We'll see that in Newton's second law later, that mass actually determines how hard it is to get something moving or to stop something or to deflect something to make it change its course. So it measures both of those things, how much matter there is in a thing, also how much inertia the object possesses. We want to be careful because in physics, when we say something is massive, doesn't necessarily mean it's very big. I could have a massive iron ball, which is very tiny, right? So massive doesn't mean size. It really just measures how much inertia the thing possesses. Basically, how much is it going to hurt you if it were to hit you in the head is what inertia measures. 1 kilogram on the Earth, how many kilos is that on the moon? More or less or the same? It's exactly the same. 1 kilogram on the Earth is exactly 1 kilogram on the moon. You might know that things weigh less on the moon, but mass is not weight. Mass is a measure of the inertia of an object. So let's be careful to make this distinction. The difference between mass and weight. Superman can lift a car, but we can't do that. Is it easier to lift a car or to push it? If your car runs out of gas, it's possible to push the car along. Um, that tells me that there's definitely a big difference between the weight of an object and the weight and the mass of the object. You see, when we say weight, weight is just another way to say gravitational pull. The weight of a thing absolutely changes depending on where you put it in the universe. If I take a car out into space, like that Tesla that's flying out there, it's weightless. It has, if it's far enough away from the Earth, it has no gravity pull on it and it weighs nothing. However, it still has inertia to it. If that car flying out in space were to hit into you, it would hurt you. So, weight is something that depends on where you put it in the universe, like what planet it's next to. Something might weigh very little on the moon, might weigh a lot on the Earth, but the mass is something which is the same no matter where you put it. Okay, so how did we come up with the definition of mass? Well, around 1800, 1 gram was defined to be 1 cubic centimeter of water. 1 centimeter cubed of pure water. That was defined to be what we mean by 1 gram. Then, once we knew what a gram was, then 1,000 of that makes a kilogram. And then they put an equivalent chunk of metal in a vault in France, and that was the standard measurement of, of mass. Our universe contains a range of different masses. A human may be around 100 kilograms. The whole galaxy that we're in is 10 to the 42 kilograms, counting all the stars and everything else. That's 10, that's 1 with 42 zeros behind it. Huge amount of mass. Compare that to an electron, which is a tiny, tiny fraction of a kilogram. Okay, that's mass. It measures the amount of matter, the inertia that an object possesses. We want to know how things move. Also, what matters is distance then. You need to have a way to define length. The metric unit of length is a meter, approximately 3 feet, roughly. So what is a meter? How is it defined? Well, we define distance in terms of how far light travels in a tiny split second. In a fraction of a second. This tiny fraction of a second right here, the distance that light goes in that split second, we define that to be a meter. Why that tiny split second? Well, because you see the meter was already determined way back when in terms of a certain distance, and so this definition just makes it universal, so that anyone in the universe could agree on or understand what we mean by 1 meter. It leads to a question, which is what is 1 second then? And we'll come to that. Centimeters are often used to measure things. 1 centimeter is just a fraction of a meter. In other words, 100 centimeters makes up 1 meter. Now, if you look at a ruler may have a marking on it that says cm. That means that the numbering on the ruler marks off centimeters. The tiny subdivisions are in millimeters. Each centimeter is subdivided down into 10 parts, which are those are the millimeters. 1,000 millimeters in a meter, 100 centimeters make up a meter. For reference, 1 inch is about 2.5 centimeters. Or, in other words, roughly speaking, 1 centimeter is about half of an inch. So you should know when you look at the ruler, these tiny subdivisions, those are not centimeters. Those are tiny little millimeters. let's practice converting units. You pause it while you calculate your height in centimeters using the conversion that 1 inch is 2.54 centimeters. I'll wait while you do that. So I hope you worked out your height in centimeters. If not, pause it and do it. So the way that you do it is, first I'm going to start with how many inches tall I am. I'm about 5'11". 5'11", that's 71 inches tall. So 71 inches. Then I have to multiply by the conversion factor that takes you from inches to centimeters. You multiply really just by the number 1, but the number 1 is 2.54 centimeters divided by 1 inch. You see, that's actually the number 1 because 2.54 centimeters is equal to 1 inch. So I'm not changing the value, I'm just converting it, translating it from one unit to another. This gives me 180 centimeters. 180 centimeters. So there you go. There you go. That's how you do it. You multiply by the right conversion factor. Notice that I had to multiply by centimeters over inches. That way the units of inches will cancel out and I get a final result measured in centimeters, which is what I want. The universe contains a huge range of distances. 10 to the 26 meters, that would be the most remote known quasar. Quasars are super bright objects, probably like black holes erupting or something like that. 10 to the 26 meters, that's 1 with 26 zeros behind it. Compared to the size of an atom, which is about 10 to the minus 10 meters. Tiny, tiny fraction, and we'll talk about the size of atoms in a later chapter. Okay, so we've done mass in kilograms, we've done length in meters, and now we need to talk about time, how time is measured. So before 1967, it was defined in terms of a solar day. In other words, 24 hours split into, each hour split into 60 minutes, each minute split into 60 seconds. It's the ancient Greeks who liked to divide things into 60s. It has lots of factors. Actually, I think it might be the Babylonians before the Greeks. That's why we use everything dividing into 60s. That's sort of an ancient way of doing it. After 1967, we came up with a more universal definition of what we mean by time. 1 second. 1 second is like 9 billion vibrations of a cesium atom. One cesium atom is the same no matter where it is in the universe, and they vibrate at a certain rate no matter where they are. And so that is a useful universal way to define what time is. We can look at some typical ages. The age of the universe, around 14 billion years, which is like 10 to the 17 seconds. 1 year, how many seconds are in a year? It turns out to be about 3 times 10 to the 7. Actually, it's about 3.1 times 10 to the 7. So it's just a mnemonic to help remember how many seconds there are in a year. It's about pi times 10 to the 7 seconds. The Big Bang was an incredibly brief instant where all the matter, all the energy in the universe was born. We now have smartphones that can take slow motion videos. In the 60s, the best you could do was about 10 to the 6th frames per second. And with that, that's a million frames per second. 1 second divided into a million intervals. You could see a bullet piercing an apple. And that was a novel thing at that time. Now we can do a lot better, and we can actually see light traveling. We can slow down our video enough to see the passage of light. That's not a million times slower, but 10 billion times slowed down. Of course, it requires super special equipment in order to do that. So inertia is the tendency to maintain motion. Something that's moving will tend to maintain the straight line motion. It also means that objects that are at rest, they maintain that motion as well. They maintain not moving. So objects at rest, they tend to stay at rest as long as there's zero force. With zero force on them, that's what happens. So you can pull a tablecloth out from under the dinnerware because the tablecloth applies very little force to the objects. There's not much friction between them. So you can yank it out and they barely move. They're at rest, very little force on them, and they tend to stay at rest. So to move further, we need to zero in on this part of it. The part about zero force. That's key because to understand whether it's how something's going to move, whether it's going to stay at rest or what, you've got to know whether there's zero force on it. So force is any push or pull on an object. And now I can push on things in different directions. I can push forwards. I can push to the side. I can push down on the floor. My feet are pushing down on the floor when I stand on the ground. Um, the force has a direction to it. Things that have a direction are called vector quantities. So a vector quantity is a measurement that you make which has two pieces to it, two ingredients. It has a magnitude, in other words, how big it is. I can push a little bit on the floor, or I can push really hard on the floor. That's the magnitude of the push. I could put a scale under my feet and measure it. But the push also has a direction. Am I pushing down on the floor? Am I pushing sideways against the wall? There's a direction to how hard I'm pushing as well. This is to distinguish from what's called a scalar quantity. A scalar quantity has only a magnitude and that's it. For example, your temperature, 98.6. There's no direction to that. It's just a number. Uh, the mass of a car. Mass has no direction. It's just its mass in kilograms. Now, the weight of a car does have a direction because it's pulled down to the earth. But mass doesn't. Mass has no direction to it at all. So a scalar quantity, it's just a number with some units like 20 kilograms or 98.6 degrees Fahrenheit, just a number. But vectors are numbers with a direction to it as well, up, down, left or right, diagonal or whatever. Okay, so net force. Force, like one force, that's good, but to look at actual objects that are around us, pick any object in your room right now, there are going to be multiple forces that are acting on it. We need to learn how to combine those forces together. So net force is the total, in other words, the combined force on a body. The total or the combined force. We use the word net like you use it with income. Net income, for example, you combine all the sources of income together. The thing is that force has a direction. It can be positive or negative. It can be up or down, and so on. So for instance, here we've got this body, this brick, that has two different forces that are acting on it. Notice the forces, they're both 5. They have a unit attached to it. We're used to measuring force in pounds, at least we are in the US. We measure force in pounds, but pounds are not the metric unit of force. The metric unit of force are called newtons. Newtons, those are the metric unit of force, the international unit of force. Didn't I just get finished saying there's only 3 things we need to know? Mass, length, and time. Well, force, it turns out, is a product of those different units. That we'll see that later in the next chapter. Okay, so when we talk about force and net force, it'll be measured in newtons. Here I've got 5 newtons and 5 newtons, both in the same direction on the brick. The net amount of force then, they add together and give us 10 newtons. If the 5 and the 5 are in opposite directions, they fight against each other, and the right way to combine them to get the net force is to do a subtraction. 5 minus 5 gives me 0 newtons. So because it has a direction to it, it has to be, you have to factor that direction in with a minus sign. Okay, so we need practice with this. Here's our brick or box. 10 newtons to the right, 5 newtons to the left. What's the net force on the brick? It's 10 to the right, so I have to add 10. But then I have to subtract 5, since it's 5 the opposite way, for a total net force of plus 5. Meaning it's the net amount of force is 5 newtons to the right. D. What if it's 15 to the right, but 20 newtons to the left? Now what's the net force? Pause it, you should figure it out on your own. So this would be minus 20 newtons plus 15 newtons. And in this case, I get minus 5 newtons. Force can be negative. Does that make sense? You can pull something with a force of minus 5. Sure. The minus sign is just telling me the direction. Since I get negative 5, that means the force is 5 newtons, but directed to the left. That's all the minus sign means. It just tells you the direction of it. It's just because force is more than a number. It's more than just magnitude. It's also a direction. Okay, so we know that things stay at rest as long as there's 0 net force acting on it. So this is called the equilibrium rule. It says that if there's no force acting on an object, then it maintains its position. Or more generally, if it's already moving, then it keeps on moving. We call this the equilibrium rule. And we'll often see it written this way in equation form. We write that the sum of all the forces is equal to 0. This letter right here is a Greek letter, capital S. It's actually called sigma. And it means you sum or add up all the forces. And the object will maintain its position if the sum of all the forces is equal to 0. Now, just like in the examples we saw, adding up all the forces might mean that some of them are negative. Like 5 this way, negative 5 adds up to 0. So for example, the painters on the platform, the combined amount of all the different forces that act must combine to 0 if the whole thing's staying at rest. Otherwise, they're falling. Okay, we'll start with simpler examples and work our way up. A string holds up a bag of flour. I want to look at the forces that act on the flour and understand how it's in equilibrium. Okay, so we do this using what's called a force or free body diagram. We draw a picture to understand how the forces are balanced on the object. So I'd like to look at the forces that act on the bag of the flour. So I just draw the flour, I free it from everything else, and I'm just going to draw the forces that act on it. First, I should have a count of how many there are. If I'm going to draw the forces, I'd better first be able to count how many forces there are so I know how many to draw. Okay, how many forces act on this bag of flour? Well, I know that the Earth's gravity pulls it downwards. So there's the weight, W. Also, there's a string attached to the top of the flower that ties it to the scale. A string applies tension to the bag of flour. So there's an upward force that acts on the flour as well. That upward force is the tension. Think of a rubber band. When you stretch a rubber band, doesn't it pull your arms inwards? And a string acts like that. It's not as stretchy, but when you pull on a string, it pulls your hands inwards as well. So when the flour hangs on it, on the string, it stretches the string ever so slightly, and the string reacts by pulling upwards on the bag. Okay, so we've got the weight and we've got the tension. They must be balanced with each other. The flour is just hanging there on the scale, not moving. And we know if something's staying at rest, what about the forces on it? They have to be balanced, right? The forces must add up to zero. I must have the total amount of force acting on the bag of flour to be zero. That means the tension minus the weight must equal zero. Or in other words, the tension must equal the weight. The tension must equal the weight. That's how the scale knows what the weight of the flour is, because the scale only just registers what tension it's pulling with. Try this one yourself. Draw the rock. The rock's hanging on a string. Draw all the forces that act on it. Step one is you got to count them. Step two, you draw them in appropriately. So pause for a second, try it yourself on a piece of paper. Just like the flour, there are exactly two forces that act on it. The weight of the earth pulling downwards, W, and the tension in the string, which pulls upwards. The string actually pulls from both ends. You know, it might rip out of the ceiling, right? If the rock's too heavy. That's because the string tension pulls inwards on both ends of the string. This one right here, that is not acting on the rock. So I don't draw it in my free body diagram. I draw only the rock. I free it from everything else when I draw the picture. And I only draw the forces that act directly on the rock. Number one, Earth's pull, that's the weight of the rock. And number two, the tension in the rope, in the string. Notice the way I drew it, both forces pulling from the center of the rock. That's to help organize the drawing, and it makes it more clear that the two forces must be balanced with each other. And I must have the tension be exactly opposite in direction and size to the weight. Okay, so we drew the flour hanging on the scale already. What about if I hang two of those bags of flour on the scale? When it's one bag, the scale tells me that it's 10 newtons of weight. When it's two bags of flour, it registers about 20 newtons of weight. How does the scale know what the total weight is of both of them? This bottom one isn't even touching the scale, so how does it know? Let's draw the forces that act when there are both bags of flour, and we'll see how this works. Let's start with the bottom weight. It's just one of the weights, which I know weighs 10 newtons. So I'm going to draw that force on it. That's the weight of it. Isn't there an upward force on it as well? Sure, there's the string that ties the two together. The string is being stretched up and down, and therefore the bottom of the string pulls up on that one. The top of the string pulls down on the other one. That's from the tension. So that bottom one, the bottom weight, has an upwards tension acting on it. Isn't that tension exactly 10 newtons? Because I know that bottom one is in equilibrium, so the forces must balance on it. Okay, this one's the weight, this one's the tension. Okay, now let's look at the top weight here, the one above it. How many forces act on this one? I'll wait while you count. Your count should have given you 3 forces. Now there's the pull of the bottom string pulling down on it with 10 newtons. It weighs 10 newtons, so there's an additional 10 Newton downward force that acts on it. So actually, there are 2 10 Newton forces pulling down on it. 10 and 10. One of them's the weight, and the other one is the tension in the string pulling down. Of course, there's also this string here that ties it to the scale. How hard is that string pulling? The top string. Well, let's see. Isn't the top one in equilibrium as well? And that means the total force on it has to be 0. So how big is this unknown force right there? If you said 20, you're right. Must be 20 newtons because it's got to balance the 2 downward pulls on it. So that's how the scale knows to read 20, because the string has to hold up 20 newtons to support everything below it. Suppose that she weighs 400 newtons. Let's use the equilibrium rule of the total force being 0 to find the tension in the rope. Remember, a rope, when you think of rope or tension, think of a rubber band. And when it stretches, it pulls inwards on both ends. So when she's hanging from this rope, she's actually being pulled up by both ends of the rope. This end and that end. So how big is the tension in the rope? Well, she weighs 400. Let's draw a free body diagram. There she is. She weighs 400. So there's a downward pull on her of 400 newtons. She's holding on to the ends of the rope. Each end pulls equally. How big must those be to hold her up? They're not both 400. That would be too much. Each one must be equal to 200. That way, the total amount of force on her, the sum of all the forces, adds up to 0. Just to be sure, let me write it out. Sum of all forces being 0. That means it's 200 upwards plus another 200 upwards with 400 downwards, that's minus 400, equals 0. That means that the tension in the rope is actually 200 newtons. Is that magic? You can hold up 400 newtons using only 200. The rope only has to pull with 200, but that's because it's a rope and it pulls on both ends. And so that's why you use a pulley. A pulley lets you hold up heavier things than you'd normally be able to do. Okay, more practice with the equilibrium rule. Find the tension in each rope. What I didn't write here yet is that the painter and the platform together weigh 1,000 newtons. Painter and platform that he's on weigh 1,000 newtons. So what must be the reading in this scale? 500. That way you've got 500 up, and 1,000 downwards, those balance. Plus 500 from the left side, plus 500 from the right side, minus 1,000 from all the weights combined to give 0. That's how I knew the one on the right must be 500 newtons. If he steps over to the right, it'll put things off balance. Suppose this one is 170. Now what's the right-hand one? Pause it, figure it out. This is practice for tests. Okay, So you've paused it, you've made an attempt to figure it out. If not, do that. Let's see how we solve it. The rule is the total of all the forces must be 0. That means 170 plus the unknown force, let's call it x, minus 1,000 must balance to 0. You solve for x. Rearrange and solve. On the left side, I get minus 830. I bring it to the right, and I get x equals 830. It's newtons. That way, the total amount of upward force is 1,000, exactly balances the 1,000 downwards. Let me remind you, if you're not comfortable with basic algebra like this, then that's telling you should, it means you need to look for some tutoring. There's online tutoring available through the library. Now, what if he goes all the way over to the right, such that the left-hand string registers 0 tension? Then the right-hand one must read 1,000. It has to read 1,000 because the total amount of force has to balance out to 0. In this case, it's 0 plus 1,000 minus 1,000 all balances out to give 0 newtons. Pete the painter weighs 500 newtons. There are 2 ways he could use a pulley to support himself. In the left-hand picture, he ties the rope around the pulley and he attaches both ends of the rope to him. In the right-hand picture, he uses the pulley, but he ties off one end to him and one end to the flagpole. Is he safe? Let's see. Let's start with the one on the right first. Pete the painter, he weighs 500. 500 downwards. In order for him to be supported, wouldn't the rope have to be able to support 500? So in the right-hand picture, the rope would have to pull up with 500 newtons. However, we're told that at maximum, the rope can only give 300 before it snaps. So this is the wrong way to do things. Physics can save your life if you know the equilibrium rule and you understand how things work here. He weighs 500. On this picture, the rope would have to pull up with 500, but it would snap before he put his full weight on it. So he'd fall. The left-hand picture is good. He weighs 500. But in this case, both ends of the rope can pull up on it. So both sides of the rope could pull up with about 250 on both sides to balance out his weight. And that's safe. The rope can withstand 250. So you see the advantage of the rope. Again, you can hold up a 500 Newton thing, but the rope, you can hold up the painter 500 Newtons, but the rope itself only has to pull with 250. That's 250 from both ends. It's kind of like if you have to hold a super heavy bag, do you hold it with one arm? No, you use both hands and then each arm is only holding up half the weight. So we decided this one's good, that one, this one's good, that one's bad.